Welcome to solverfy.
All right, so problem number 8 wants you to work out what magnetic field intensity is needed for the 1 kilometer radius Fermilab synchrotron to accelerate protons to 1 tera electron volt. So first thing we need to look at is the energy of a 1 tera electron proton is very, very high energy, so it's going to be relativistic. So we use the relativistic total energy equation here, p squared c squared plus the rest mass squared. So the kinetic energy, the square root of the kinetic energy squared plus the rest mass squared. So now the rest mass of a proton is 0.938 giga electron volts, or 938 mega electron volts, which is much, much less than the 1 TeV proton that are in this problem. So because of that, the kinetic energy term will outshadow, will overtake the rest mass term here. So this can basically be considered zero. And we can say the total energy is just the kinetic energy, which is equal to P times C. So now for a synchrotron, the velocity of the particle is given by Q, the charge of the particle, times the magnetic field of the particle, times the radius of the ring, divided by the mass of the particle. So solving for B, we can say, let's solve for MV. So mass times velocity is equal to QBR. So now the reason we did this is because, M for mass, this is just the momentum. So the momentum is equal to QBR. Now multiplying both sides by, since energy is equal to P times C, and the momentum, so we can solve for the momentum here. The momentum is equal to E over C. We then say E over C is equal to QBR. And then now rearranging this and solving for B, we get the magnetic field B is equal to the energy that you want to reach, the maximum energy, divided by the charge of the particle times the radius of the ring times the speed of light. Now we can plug all of the things that we know in. So let's do that. So B is equal to 1.0 times 10 to the 12th electron volts, or 1 tera electron volt, times, we want to convert this to joules because radius is in meters, C is in meters per second. So we want to be in those units. So 1.6 times 10 to the minus 19 joules per electron volt, divided by the charge of an electron, or I'm sorry, the charge of a proton in this particular, it's a charge of a proton, which is just the positive charge of an electron, which is 1.60 times 10 to the minus 19 coulombs, times the radius of the ring, which is 1.0 times 10 to the third meters times the speed of light, which is 3.00 times 10 to the 8th meters per second. Gives you a value of B. So the magnetic field strength you would need to accelerate a proton in a 1 kilometer ring, 1 kilometer radius ring, is going to be equal to 3.3 Tesla, which is a pretty strong magnet. But not extremely strong. you know, an MRI magnet's about one to 2 Tesla. So, but still a pretty strong magnet.